Good morning, Algebra 1 class. I'm coming at you again from the elephant schoolroom to do another lesson on video. Since we had to miss class on Friday, I thought this would again be the easiest way to make it up. Just kind of allows you all to do the lesson and the homework on your own time, which works out great for most of us who have busy schedules. We're going to follow the notes for week 20, just like we were in class. We'll be covering sections 8.3, 8.4, and 8.5. This particular lesson is a little bit easier than a couple of the lessons we've had just in the past 2-3 weeks, which is nice. Gives you a little bit of a breather. Some of it is stuff I'm sure you've seen before, like scientific notation. We won't finish the chapter this week. Chapter 8 is quite long. So we'll go over just these 3 sections today, and then when we come back to class on Friday, we'll go through the next 3 sections of Chapter 8. And if you have any questions about this video or the homework from this week's lesson, there should be plenty of time to ask them on Friday. So I hope you'll make note of them if you have questions. I'd be happy to answer them. Okay, so let's go to your notes, page 1. And we're starting with scientific notation. Now, scientific notation is probably something you've seen already, but it's numbers that look like this. Let's say you have 1.23 times 10 to the 6th power. This is basically a shorthand approach to writing numbers that are either way too large or way too small to be represented in standard form. Standard form would be just normal form without all these decimals and exponents. You see this a lot in scientific literature. For example, the distance between stars is obviously an incredibly huge number. So in a scientific textbook, they're not going to write that number in standard form with all the zeros needed to represent that incredibly vast number. They would write it in scientific notation, and they can use this exponent to show you how many zeros you would have to write. It gives you an idea how huge it is. It's also used to write incredibly small numbers, numbers so tiny that they'd have to have lots of zeros to the right of the decimal place. You know, you can have way more than this, but let's say you just start with something like this, 17. This is obviously quite a small number. And then if you write it in scientific notation, it's just a shorthand, easier way, especially in your science curriculum, to represent a very small number. Like, let's say it could be the weight of a molecule. When you get into chemistry class, you'll talk a lot about the weight of different types of molecules, and you might see a lot of your numbers written in scientific notation for that reason. All right, so what we need to know is how to take numbers from standard form and write them in scientific notation, and then how to go back to standard form again. We'll practice that right now. Let's take a number like 750 billion, right? That's quite a large number, isn't it? And we want to write it in scientific notation. Now, what you look for is you want to take a number from this rather large number, and specifically you want that number to be between 1 and 10. And then you're going to write it times 10 to a particular exponent. And that exponent will tell you how many places you had to move the decimal point in order to consolidate it into a number between 1 and 10. So if we look at this large number, and the decimal point at this time is way over here at the right, you want to move that decimal point so that you create a number between 1 and 10. Now if I move it just to here, the number I'd create is 750, and right, that's way too big. If I move it in again, now I've got 75, still too big. If I move it in one more time, There's the sweet spot right there, 7.5. That's a number between 1 and 10. So 7.5 is the number I'm going to use. I'm basically moving the decimal point there. But I need to reflect that change by putting the number of decimal points I moved it as an exponent. So let's count how many places I moved it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to make that exponent a positive 11 because what I did is took a very large number and wrote it in a smaller way. But that exponent needs to be positive because I need to tell my reader that they would need to move the decimal point to the right or in a positive way to get back to the original number. So obviously you'd see the pattern here. If you're taking a large number and writing it in scientific notation, the scientific notation would be as a positive exponent in order to show that you would move it back to the positive direction, back to the right if you want to go back to standard form. And consequently, if you're taking a very, very small number and writing it in scientific notation, you would use a negative exponent to show your reader how to get back to the original really, really small number, right? All right, so let's do a small number to show the difference. Let's take 0.000000585. We're going to write that in scientific notation. Again, first we want to locate a number between 1 and 10. So as I move my decimal point over, still not there, right there. If I go farther, I end up with a number larger than 10. So 5.85 is a number between 1 and 10. And now I need to reflect how much I moved my decimal point. So let's count 1, 2, 3, 4, 5, 6, 7. Now I'm going to make that exponent negative to the negative 7th because that would tell my reader that if they want to take this number and put it back in its original standard form, they would need to move the decimal to the negative direction 7 places. Okay, going back to your notes, let's do a couple of the examples that your notes give us. First we have express each number in standard notation. So here we have 7.48 times 10 to the negative third. All right, what we're going to do is move the decimal point the number of spaces the exponent tells us to move it, and in the direction the exponent tells us to move it. The exponent is negative, so we're going to move the decimal in the negative direction 3 places. So I'm going to give myself a little bit of room, and I'm going to start here and go 1, 2, 3, and then leave the decimal point there. Now what do you do with those empty spaces? You simply fill them with zeros. So my answer is 0.00748. All right, let's do another one. This one is written in scientific notation, 2.19 times 10 to the 5th. All right, this one obviously is telling us to move the decimal point in the positive direction 5 places. So I'm going to give myself a little bit of room, and I'm going to take the decimal and go 1, 2, 3, 4, 5. Fill any blank spots with zeros. And then it's always a good habit to add your commas as well every 3 places. So this represents 219,000. Going back the other way, we're going to take numbers in standard form and put them in scientific notation. Here we have 0 point and then 6 zeros, I believe. 1, 2, 3, 4, 5, 6, 6, 7, 2. So quite a little itty bitty number. First we want to find a number between 1 and 10. So as I move my decimal place over, I won't come to that number until I get right here. 6.72. And then I'm going to multiply by 10 to an exponent, and that exponent needs to be negative because I took a very small number and wrote it in scientific notation. I want to designate that my decimal point would go negative again. And let's see how many places I had to move it. 1, 2, 3, 4, 5, 6, 7. So to the negative 7th power. Let's do another one. Here we have with 9 zeros. See if I can smush it in there. Oh, there we go. A little smushed 0 at the very end. All right, we want to find a number between 1 and 10. So if our decimal point is all the way here on the right, we're going to move it until we get right here. 3.022 would be the number between 1 and 10 that we could create. So 3.022 times 10 to the what? How many places did I move it? Well, 3, 6, 9, 10, 11, 12. And that exponent would be positive, right? Because I had to move it in this direction. So I want to tell my reader that in order to go back, you'd have to move it 12 places in the positive direction. Okay, let's do example number 3. Read it out loud first. This is just going to give us a little practice putting numbers in scientific notation and then back to standard, back and forth. The Sporting Goods Manufacturers Association reported that in 2000, women spent $4.4 billion on 124 million pairs of shoes. Men, which this kind of surprised me, spent $8.3 billion on 169 million pairs of shoes. Now, isn't that interesting? I would have thought women would have spent a lot more money and had a lot higher number of shoes. But I can imagine that the much larger total is because men's shoes are usually a lot more expensive, right? If you have any kind of like sporting shoe, it's usually a lot more expensive than a lot of kind of fashionable shoes for women. So there you go. That might be why. Let's write these numbers first in standard form, and then we'll turn them into scientific notation. Let's start with the 4.4 billion that women spent on shoes. So let's take the women's numbers. 4.4 billion would be $4,400,000,000. And that was on 124 million pairs of shoes. Quite a lot. All right, let's first, before we put the men's totals on there, the problem asks us to turn that into scientific notation. So let's take this first number here. We'd want to move the decimal point until we get to a number between 1 and 10, 4.4, and then express the exponent as 1, 2, 3, 4, 5, 6, 7, 8, 9, and a positive 9. All right, here we'd want to move it to between the 1 and the 2 to create 1.24 times 10 to the 3, 6, 7, 8. All righty, there we go. Let's go to the men's totals. 3, 4, 6, 7, 8. Okay. I was just recounting, making sure I did that one right. Let's go to the men's totals. They spent 8.3 billion. So here we have 8,300,000,000. My goodness. Dollars on shoes, and they spent it on 169 million pairs. All right, let's turn those numbers into scientific notation. We'll do this pretty fast because I'm sure you're getting the hang of it. For the 8.3 billion, we're going to take our decimal point and put it here. 8.3 times 10 to the, well, we moved it in 3, 6, 9. And then for 169 million, our decimal point would go right here. 1.69 times 10 to the 3, 6, 7, 8. 8th power. All right, I think we've got that down. Let's go to the next page, and we're going to learn how to multiply or divide numbers that are in scientific notation. So they're in this form. We need to either multiply them by each other or divide them. 2 basic steps. All right, if you're going to be multiplying, 2 steps to follow. And if you're going to be dividing numbers in scientific notation, there are also 2 steps to follow. All right, the first step when multiplying would be to multiply the constants. Now, the constants are basically the numerical part of the number. The part, let me write an example right here. Let's say we have 7.24 times 10 to the 11th power. That's a number in scientific notation. The constant is this part right here, the number in regular number form, right? You're going to multiply the pieces of the numbers here. And then you're going to add the exponents. So you would be adding the exponents from scientific notation. Now when you're dividing, you're going to do basically the exact opposite. You're going to divide the constants and rather than add the exponents, when you're dividing, you'll be subtracting them. Subtract the exponents. All right, so those are your 2 steps for each of those cases. Let's do a couple of them so you can see how it goes. Example number 4 tells us to multiply the number 7 times 10 to the negative 6th power by 4.3 times 10 to the 12th power. Express the result in scientific and standard notation. So our answer needs to basically represent both types. All right, remember our 2-step process. We're going to multiply the constants. So we're going to multiply 7 times 4.3, and then we're going to add the exponents. We'll add negative 6 and 12. All right, so if I take 7 times 4.3, I'll get 30.1, and then times 10 to the negative 6 plus 12 is positive 6. All right, now I like to leave my answer just like that, but sometimes after you've multiplied or divided, the answer that you got isn't in scientific notation anymore. There's just one little thing wrong with it. Can any of you spot it? This part looks fine, but what's wrong over here? Well, this number is not between 1 and 10, and to be in true scientific notation, it needs to be between 1 and 10. Now that's a pretty easy fix, right? If we want to just take that decimal point, we can move it over so that now it's at 3.01. But what we need to do is represent that change over here. We need to show that we already moved it one place to the left, and so to go back to the right, we need to represent that change right there by adding another number, adding another 1 to the exponent here. So this would come to 3.01 times 10 to the 7th power. Now, I like to write a little bit of a cheat sheet for how to represent that change. If, in order to put your final answer in scientific notation, you had to move the decimal to the left, like I just did, it's going to increase your exponent. So you're going to add the change to your exponent. If, in order to put it in correct scientific notation, you had to move it to the right, it will decrease your exponent. So then you would, of course, subtract your movement from the exponent, from your answer. All right, let's do another example. This one's dividing. We're going to take 6.4 times 10 to the 4th power and divide it by 1.6 times 10 to the 7th power. All right, remembering our two-step process, we're going to divide the constants. So we're going to take 6.4 and divide by 1.6. In that case, we'll get 4. And then we're going to subtract the exponents. Now you always subtract the bottom exponent from the top. So essentially you're going to take 4 minus 7. 4 minus 7 would obviously come to a negative number, negative 3. So your new exponent is negative 3. Our answer is 4 times 10 to the negative 3rd power. Then we look at our answer and we make sure it's in scientific notation, that we don't need to move the decimal point over here at all. And in this case, 4 is okay. 4 is a number between 1 and 10, so we don't need to move it. We can leave this alone, and there's our final answer. All right, let's go ahead and move on to section 8.4. Oh, wait, before we do that, stop right there. It told me on those last two examples to write them both in scientific notation and in standard notation. So let's go back to my two answers. 3.01 times 10 to the 7th power, and also I had 4 times 10 to the negative 3rd. I'm breaking my own rules. I told you you had to write it both ways, and then I tried to get out of it and only write it once. I'm sorry about that. So let's go back. Those are my two answers in scientific notation. I need to write them both in standard form as well, as the problem asked me to do. So here, to write it in standard form, I'm going to take 3.01 and move that decimal point to the right 7 places. 1, 2, 3, 4, 5, 6, 7. Fill those little empty places in with zeros and add some commas to make it look nice. So 30,100,000 is my number in standard form. And then to write this number, here I've got the number 4 with the decimal point, of course, right there. I need to move it in the negative direction 3 places. So 1, 2, 3.004, or 4,000ths. All right, now we can move on to section 8.4, polynomials. Okay, we learned what a monomial is last week. Let's review it real quick. A monomial can be a number, like 5. It can be a variable, like x, or it can be a product. Notice I didn't say it could be a quotient. We do leave quotients out of being monomials. That turns it into numbers that are different, higher order than what we'll deal with here in Algebra 1. So notice it's just a product, the product of any combination of numbers and variables. So for example, we could have numbers like 5x, or 100xy, or 3 2xy squared z cubed. Those are all examples of monomials because they're made of either a single number, a single variable, or a product of numbers and variables. Where you start getting into higher order polynomials is when you insert either a plus sign or a minus sign into the mix. And then you no longer have monomials, right? You have something larger. So let's look at those larger polynomials. Let's say you have 7x plus 10y. All right, we know that's not a monomial, mono for one anymore, because we have that plus sign. Now we have 7x is one particular monomial, and 10y is another. So this entire expression is a two-term polynomial, or more specifically, a binomial. All right, let's add on to this. Let's say I have 7x plus 10y plus 14z squared. In this case, I have 1, 2, 3 terms. That's a trinomial. All right, let's look at examples 1 through, let's see, well, it's example 1 split up into 4 pieces. And answer the question, state whether each expression is a polynomial. If it is a polynomial, identify it as a monomial, binomial, or trinomial. Okay. All right, I do want to point out that a polynomial encompasses all of these types of terms that we've studied already. A polynomial can be a monomial. It can be a binomial. It can be a trinomial, or any of these other higher order ones. So let's look at example A. You have the expression 6 minus 4. All right, that's kind of a simple polynomial, but in this stage, before trying to simplify it or make it something that it's not right now, notice this is made up of 2 distinct terms, 6 and 4, and they've been separated by this negative. So in this case, the answer to, first of all, is it a polynomial? The answer is yes. And specifically, what type is it? Well, it has 2 terms, so it's a binomial. Okay, let's go to the next one. On the next page, we have x squared plus 2xy minus 7. All right, notice we have 2 dividers in this case, a plus and a minus. So this has separated this particular polynomial into 3 distinct terms. So our answer to this question, first of all, is it a polynomial? We would answer yes. And what type is it? It's a trinomial. Okay, C. All right, here's a little bit of a tricky one because we have 14d plus 19e squared over 5d to the 4th. All right, we're discussing specifically polynomials. And remember, with polynomials, we are allowed to take the product of different numbers and variables, but not the quotient. So in this case, notice right away we've got a division bar, we've got a number in the denominator. So right away, the fact that there's division in this particular expression disqualifies it from being a polynomial. So in answer to the question, is this a polynomial, we get to answer with a big no. And we don't have to go any farther than that. We don't have to identify it as something more specific because it's not a polynomial to begin with. All right, let's go to the next one. 26b to the 5th power. First of all, is this a polynomial? Yes, even though it's the simplest type possible. And it's just a one-term polynomial, so specifically it's a monomial. Okay, moving on. Here you have a little bit of a diagram. With a rectangular piece, and you've divided it into kind of a triangular bottom. And then we have some different lengths designated for us. The length of this bottom base is represented just by B, obviously B for base. And then we've split the height into H for the length from the base to this intersection here, and then another H for here to here. So what that's essentially saying is you have the height of the triangle, and then the height of the rectangle would basically be twice the height of the triangle, because look, they're both assigned the same variable. That means that they're equal to one another. So you have height and then basically 2 times height for the length of the rectangle, the larger figure. Okay, what's the problem asking us to do? Write a polynomial to represent the area of the shaded region. All right, they shaded this region here. So everything but the triangle. So if we want to write a polynomial that represents the area of the shaded, what we need to do is designate how to write the area that represents the whole entire figure and subtract from it the area of the triangle. And that would give us an expression that represents just the shaded portion of that rectangle. All right, so in order to write an expression that represents the area of the rectangle, we need to take the base times the height of the rectangle. Now I already kind of pointed out that the height of this rectangle is represented by 2 times h, because you basically would have to add that height twice. So the base times 2 times h. Now this looks a little funny. We're not used to writing the constant in the middle, kind of sandwiched in between other variables. And so we can switch that order to make it look a little more proper, because remember, when you're multiplying values, the order that you multiply them does not matter, does not affect the outcome. So what I can do is instead write the 2 at the beginning as the coefficient where it looks better, and then write base times height following. All right, so 2 times base times height would represent the area of the entire rectangle, and we're going to subtract from that the area of the triangle. Now, this is assuming that you know what the formula is for the area of a triangle. I'm sure you know it already, but in case it's gotten a little fuzzy, that area is 1/2 the base times the height. All right, so let's look at the triangle we're given here. It's base times height is all we really need to know. So we're going to take 1/2 the base times the height. And there is our final answer. Notice we're not given any values to plug in for base or height. We don't really get to solve this particular problem. We just get to write an expression that represents how you would solve. And in this case, notice we have a polynomial, and specifically it's made of 2 distinct terms separated by a negative, so it's a binomial to be precise. All right, let's move on. To the middle of page 3, we're going to talk about the degree of a monomial, and then how to find the degree of a polynomial. All right, let's say you have a number like 13x squared y z. All right, notice this is made up of constants as well as variables. And on a number like this, you might be asked to find the degree. The degree can be found by adding all of the exponents, the sum of all the exponents. So in the case of 13x squared yz, we would want to add the exponents. Now, what do you do if there's no exponent written there? Well, we've studied this before. It's always understood to be 1. And so it might help to go ahead and write that in, just so you don't forget to add those ones in. It'd be really easy to forget them. All right, so you're going to add 2 plus 1 plus 1, which is, of course, 4. So this particular monomial is a 4th degree monomial. Now, one thing to watch for is they might ask you to find the degree of a particular monomial or polynomial in terms of x, and you want to watch for that particular expression in terms of x. When you see that expression, a big red light should go off, because they want you to find the degree of this monomial, but they only want you to look at the x exponents. They basically want you to ignore all the other variables and put all your focus on x. So going back to this one, if we were asked to find the degree of this monomial in terms of x, we would only look at the x variables. We'd ignore the other ones. And this particular monomial would be a 2nd degree monomial in terms of x. So you do want to watch for that on your homework, for that expression, because then you have to do something a little different. Only count the x variables and ignore everything else. All right, I'm starting to repeat myself again. I know I do that when I'm doing this on video, because I can't look at all your bright smiling faces, and I can't see you nodding enthusiastically and showing me, yeah, we get it, it's just a camera looking back at me. And so I have to sort of overcompensate and repeat myself a couple of different times. And I apologize for that. We'll move on, because I'm sure you get it. Let's look at the degree of a polynomial. So now we're not looking at just one term all by itself. We're going to look at an expression that has more than one term. Here's an example. Let's say we have 15 plus 7x squared plus 3x squared y squared z. All right? And we're asked to find the degree of the polynomial. So what we want to do is look at the entire polynomial and determine what degree it has. Well, what you do in this case is you assign a degree to each individual term, and then whatever term is the biggest, that is your answer for the entire thing. All right, so let's look at each individual term. 15 doesn't have any variables at all, so it has no exponents to begin with, so it has a degree of 0. Let's look at 7x squared. Well, we count the exponents. It has a degree of 2. Now we go over here, and we have a degree of 2, a degree of 2, and a degree of 1, because of course, remember, when nothing's written there, it's understood to be 1. So we add 2 plus 1, and that's a degree of 5. All right, now I'm going to ask you a very difficult question. What is the largest number here? 0, 2, or 5? And I hope you all answered 5. So because 5 is the greatest. The 5th degree term is the largest degree term of the entire polynomial. We assign a 5th degree for the entire thing. All right? Let's do a few more examples, and these ones are on your notes so you can follow along. Let's do examples A, B, and C. It says find the degree of each polynomial. Here's example A, 12 plus 5b plus 6bc plus 8bc squared. Goodness, I'm running out of room. Got to start these farther this direction. All right, first let's assign degrees for each individual. 0, 1, 2, and 3. And so the degree of this polynomial is a 3rd degree polynomial. So we always take the biggest one. All right, let's do another one. Here we have 9x squared minus 2x minus 4. Let's assign our degrees. 2, just 1, and 0. So this would be a 2nd degree polynomial. And one more. We have 14 g squared h to the 5th I. All right, this particular polynomial is just a one-term polynomial, so we'll simply count its exponents, and that will be the degree measure for the entire thing, obviously. All right, so we have 2 and 5, and there's nothing written here, so we assign it a 1. 2 plus 5 plus 1 is 8. So this is an 8th degree monomial. All right, now look at examples 4 and 5. And notice you get that pesky little expression of the powers of x. I'm going to read the entire thing and see if you catch it. Arrange the terms of each polynomial so that the powers of x are in ascending order. Ascending obviously means go up. So you're going to start with the smallest and work your way to the largest. But we have to pay particular attention to the fact that it asked only for the powers of x, meaning that as we assign degree values for each term, we're only going to look at x and we're going to ignore any other variables. Now, some of them will only have terms of x, so that will be easy, right? And others will have other variables that we basically have to ignore. All right, so look at example A. We have 16 plus 14x cubed plus 2x minus x squared. All right, first let's assign the degrees. We're only looking in terms of x. Fortunately for us on this one, there are only x variables. That makes it a little easier for our first one. 16 has a degree value of 0. 14x cubed has a degree value of 3. 2x has a degree value of 1. And x squared has a degree value of 2. On this particular problem, it asked us to rearrange the order of this polynomial so that the powers of x are in ascending order. So we want to start with the smallest and work our way up to the largest. So obviously we're going to start with 16, it's already in the right spot, and then go to 2x, and then to negative x squared, and finally to 14x cubed. So it looked like this: 16 plus 2x minus x squared plus 14x cubed. There we have it. Let's do another one. We have 7y squared plus 4x cubed plus 2xy cubed and minus x squared y squared. All right, and again, our instructions are to arrange the terms of the polynomial so that the powers of x are in ascending order. So we're only going to pay attention to the x exponents and nothing else. So let's look at this first term. There aren't any powers of x in it, and we ignore the y's, so this particular first term has a degree value of 0 when we're only looking at powers of x. Go to the next one. Well, here we have a power of x with an exponent of 3, so this has a degree value of 3. Over here, we're only going to pay attention to x and ignore y cubed, so this particular term has a degree value of only 1. And on this one, we're going to only look at x, again, ignore y squared, so x squared gives it a degree value of 2. We're going to rewrite this problem so that each particular term comes in order of its degree value. So we're going to go from 0 to 1, 2, and then 3. All right, so it would start with, well, again, that one's in the right spot. And we'll go to the first degree, second degree, and finally third degree in terms of x. Okay? Example 5 asks us to do the exact same thing except to write it in descending order. That means now we're going to start with the largest and go down. So look at example 5. It says to arrange the terms of the polynomial so that the powers of x are in descending order. So first let's write the polynomial. 8 plus 7x squared minus 12xy cubed minus 4x cubed y. All right, again, it does specifically say the powers of x, so we're paying attention only to x, ignoring everything else, and we'll assign our degree value and then put them in the right order. So let's start with 8. Well, that's a degree value of 0. 7x squared, if we pay attention only to x, well, that's a degree value of 2. Negative 12xy cubed, only pay attention to x, so it has a degree value of 1. And this last one, if we're only paying attention to x, has a degree value of 3. All right, now we need to write these in descending order. So we're going to start with the greatest and work our way down to the least. So we're going to start with negative 4x cubed y plus 7x squared minus 12xy cubed plus 8. And it's that simple. All right, let's go to the next page. We're not going to do example B because it's almost exactly the exact same problem. We're going to move on to section 8.5, adding and subtracting polynomials. All right, when you add and subtract polynomials, it's actually quite easy. You can only add or subtract terms that are alike. So just to review the concept of like terms have to have the same variables, and those variables have to be in the same degree. So if your variables and degrees match, obviously it means you have like terms, and you can add or subtract their coefficients. Okay, so let's do an example of that. Example number 1 has this expression 7y squared plus 2y minus 3. And we're supposed to add to it another expression, which is 2 minus 4y plus 5y squared. So we're essentially taking this polynomial and adding it to this polynomial. Now, what we have to be careful to do is we can only add the terms that are like terms. So what I'm going to do is I'm going to take the second expression they gave me, and I'm going to basically write it as columns underneath this expression, and I'm going to line them up in such a way that the like terms are creating columns. So let's look at the number 2. The only number that it's alike to is -3, right? Because they're both whole numbers. So I'm going to add the 2 here. Then if I look at -4y, the term that it's alike to is +2y because they're made up of the same variable to the same degree. So I'm going to put -4y here. Cross it out, so don't try to add it twice or anything like that. And then +5y squared is obviously alike to 7y squared, so I'm going to add that here. Now, since I've already got it written where it needs to be, I can erase it right there. Write a big addition bar, a big plus sign there, and then essentially you just add your columns. Once you've got them lined up correctly in like term columns, you can add them. You do that by adding the coefficients. So 7 plus 5 is 12, so we've got 12y squared. +2 and -4 would come to -2y, and -3 plus 2 is -1. And there's your final answer once you've combined all the like terms. Now what happens if you are subtracting the second polynomial? Well, you essentially do the exact same thing as I just did on this example where you're adding them, but you have to change the sign of all the terms in the second polynomial. And I'll show you why. Let's look at example 2. We have 6y squared plus 8y to the 4th minus 5y. All right, there's our first polynomial. And from this, we are subtracting a second polynomial. And I'm going to write it here. 9y squared, or I'm sorry, 9y to the 4th minus 7y plus 2y squared. Okay, so what this problem is asking us to do is take this polynomial and subtract from it this polynomial. Now what we want to do before we start lining up our columns is, because they're asking us to subtract the second polynomial, we need to change the sign of every term on the inside of the second polynomial, because that negative will be applied to each one of those terms. And remember, a negative will change the sign of each term. So let's do that as a first step so we don't forget about that in our hurry to start adding like terms. So positive 9 to the 4th would become negative. Negative 7y would become positive, and positive 2y squared would become negative. And then we can really kind of get rid of that negative symbol because we've already reflected it in each of those terms. Now, once that step's out of the way, you can do exactly the same thing we did on the last example. Line up like terms in columns and then we'll add them together. So let's look at negative y to the 4th. Well, it would be alike to this middle term, so I'm going to write it right here and then cross it out. 7y would be alike to this term, and negative 2y squared would go right here. And now we can get rid of this and add them together. So let's add our first column. 6y squared minus 2y squared would come to 4y squared. 8y to the 4th minus 9y to the 4th would be 1y to the 4th, or just y to the 4th. Whichever way you want to write it is fine. I'll write it with the 1. And then, oh, I'm sorry, with the negative 1. Apologize for that. You see, even teachers make mistakes sometimes too. And then my last column would be negative 5y and positive 7y. So that would come to negative 2, or I'm sorry, positive 2. Why? I think my brain is getting a little bit tired. Notice that I added the coefficients. Let's look at that last one. Added the coefficients, so I have negative 5 and positive 7 to give me a positive 2. And then I didn't change the variables at all. Once you get to this stage, you're simply adding or subtracting the coefficients and leaving the variables alone. All right, I'm going to do one more example of that since I was kind of getting a little sloppy on my signs with that first one. Let's do another example and just make sure it's nice and clean. Let's do example number 3. It's a word problem, but we're really asked to do the exact same thing. I'm going to read it out loud. The measure of the perimeter of a triangle shown is 37s plus 42. Okay, let's draw this triangle so you can see what I mean. We are given the length of this side as a binomial, 14s plus 16, and then the length of this side is 10s plus 20. Okay. It tells us in the given information that the perimeter of that triangle, so that's the distance all the way around. Let's say if I were starting right here and traveling around that triangle, the distance all the way around it is represented by 37s plus 42. All right, so in this case, it's asking us, first of all, to find the polynomial that represents the third side of the triangle. So this mystery side right here, what is represented there? Well, as I'm sure you've kind of already guessed, what you're going to do is take the measure that represents the entire perimeter, the distance all the way around, and subtract each of those two known sides. Once you do that, you'll be left with an expression that represents the third side. So we're going to split this up into two separate problems. We're going to take 37s plus 42, and first we're going to subtract 14s plus 16. All right, so let's write 37s plus 42 minus 14s plus 16. Now remember, whenever you're subtracting a polynomial, you have to change the sign of both of any of the terms on the interior. So this would become negative 14s, and this one would become negative 16. And then we don't need to worry about that negative on the outside anymore because we've reflected it on the inside. All right, then we line up like terms. So negative 14s would obviously be alike to 37s, and negative 16 would be alike to positive 42. So I'm going to give myself room to write that. All right, then we'll use our bar, and we're basically going to add our columns together. Add the S column and then add the whole number column. All right, now paying careful attention to our signs, we have 37 minus 14. Well, that would come to 23, positive 23, and then S. Remember, the variable kind of comes through unchanged. And then 42 minus 16. Well, what would that come to? Let's go ahead and borrow, just because we want to make sure we don't make any careless mistakes and forget something. So we're going to borrow here, and we get 12 minus 6 is, of course, 6, and 3 minus 1 is 2. So our answer there is positive 26. All right, so now we've taken the value of the entire perimeter and subtracted the first side and gotten this value as an answer. Now we need to take that value and subtract the other known side, and that will give us our final answer. So what I'm going to do is write this value up here at the top so that we have room to work with it. I have 23s plus 26. And I'm going to write the value of that third side, or I'm sorry, that second known side. And that's going to be 10s plus 20. So we're subtracting from this value 10s plus 20. All right, again, remember when you're subtracting a polynomial, that value is going to get a different sign for each term. Then you're going to take each of those values and line them up with their correct like term. 23s and negative 10s are obviously alike. And negative 20 is alike to 26. We're going to add them together. 23 minus 10 is, of course, 13s. And 26 minus 20 is 6, positive 6. And our final answer. The final answer represents the length of that third side. We took the length of the perimeter and subtracted the lengths of the two known sides to find an expression that represents the third side. All right, the final thing we're asked to do is find the length of the third side of that triangle if s is equal to 3. So now they've handed us the key to unlocking all of those sides. We're supposed to find the length of that third side. We have it here as an algebraic expression. And now what we can do is substitute the value of s, which is 3, put it into our algebraic expression, and that will churn out the length of the third side for us. So we're going to take 13 times 3 and add 6. I'm going to give myself a little bit of room to work. We have 13 times 3, 39, plus 6 is equal to 45. The length of the third side is 45. All right, that concludes all the new material for week 20. I think, like I said at the beginning of the chapter, that means you can do all your week 20 homework before Friday. That would be section 8.3, a practice quiz, section 8.4, and section 8.5. Then we'll finish up chapter 8 later on, and your test will be in a couple of weeks. Please email me or call me if you have any questions, and I look forward to seeing you all again Friday. Thanks. Bye.